Okay, so section 2.5 part 2 is limits at infinity. So when we are taking the limit of a function as x approaches positive or negative infinity. And when you see limits at infinity, I want you to think end behavior of the graph of a function. And when you think end behavior of the graph of a function, I want you to now think limits at infinity. So when we take a limit of a function at infinity, we're interested in the end behavior of the graph. So as x gets large, what's happening to the y value? Or as x gets very small, infinitely small, what's happening to the y values of the function? So our analysis for the end behavior of a function can be written by taking the limit of the function as x approaches positive and negative infinity. So we're going to go through these first limits here without using a calculator by doing some analysis and recalling some of our pre-calc knowledge. So this first limit that we're taking is of a polynomial function, and you guys remember that polynomial functions are smooth continuous functions. And from pre-calc, when you guys were sketching polynomial functions, you may remember that you determine the end behavior of the function by analyzing the degree of the polynomial, so whether it was an even or odd degree. The degree of this polynomial is 5. And then you looked at the sign of the leading coefficient. So the leading coefficient here is a positive 3. Okay, so because this is an odd degree polynomial with a positive leading coefficient, that means the end behavior for this polynomial is like a line with a positive slope. Meaning, as x approaches positive infinity, the function will end up also approaching positive infinity. And then as x approaches negative infinity, the function will also approach negative infinity. If this had been an odd degree polynomial with, say, a negative leading coefficient, then the end behavior would have been like a line with a negative slope, and we would have had the opposite limits. Or if we had an even degree polynomial with a positive leading coefficient, then the end behavior would be like a quadratic with a positive leading coefficient. And then if it were an even degree polynomial with a negative leading coefficient, our end behavior would have been like a quadratic with a negative leading coefficient that has a vertical reflection. Okay, so for the limit of, as x approaches infinity for e to the negative x, let's first remind ourselves what the graph of y equals e to the x looks like. And if you don't remember, that's okay. We can create a table of values to help us. Okay, so for y equals e to the x, if we were to make t-chart, and substitute 0 in for x, we would get 1 for y. If we substitute 1 in, we would get e for y, and e is approximately 2.71. Okay, if we substitute 2 in, we would get e squared. So as x approaches, or as x gets larger, okay, the y values are going to continue to increase. And then if we were to substitute a negative 1 in for x, that would be 1 over e to the first. Okay, so 1 over 2.71. So the values are going to get smaller and smaller and smaller and approach 0 as x approaches negative infinity. Now we want to take the limit of e to the negative x. So again, falling back on our pre-calc knowledge, when the argument of the function, of the parent function, is being multiplied by a negative, that is a horizontal reflection. So e to the negative x will be e to the x horizontally reflected, or reflected across the y-axis. So it'll end up looking something like that. So you can see now that with our graph, as x approaches positive infinity, the limit of e to the negative x will actually be 0. And you may remember that we can also rewrite e to the negative x as 1 over e to the x, where as x approaches infinity, so that as you're substituting larger and larger values in for x, the denominator is going to keep growing and growing and growing while the numerator can't keep up, meaning that this limit 1 over e to the x will end up approaching 0. Okay, and then e to the limit of e to the negative x as x approaches negative infinity, we can see from our graph that will be positive infinity. If you think about substituting smaller and smaller values in for x, like negative 100, negative 1,000, negative 1 million, because of this negative, okay, then you'll end up raising e to larger and larger powers, meaning our y values will end up approaching infinity. Okay, so again, falling back on your pre-calc trig knowledge, let's think about the graph of sine. I'm just going to throw a sketch of the graph of sine on here. Oops. And remember that sine oscillates back and forth between 1 and negative 1. Okay, so as x approaches positive infinity, there's no way to know that the graph will approach, whether the graph will approach a single value, because the graph is just bouncing back and forth between negative 1 and 1. So this limit is a DNE, and I'm just going to write underneath it because oscillating between negative 1 and 1. Now, next limit is interesting because you guys have never had to graph x times sine of x by hand, but you do know what the graph of y equals to x looks like, and you know what the graph, hey.
Hi, do you know where Miss Phillips is? If she's here still?
She is teaching right now. She teaches H.
Okay, thank you.
You're welcome. Sorry about that. So you guys know what the graph of y equals to x looks like, and you know what the graph of sine of x looks like. So sine of x bounces back and forth between negative 1 and 1. Well, let's think about if we are substituting smaller and smaller values in for x, okay? Basically, this piece would be giving us values between negative 1 and 1, and then this piece will just keep getting smaller and smaller and smaller. So what happens is if this is y equals to negative x and this is y equals to x, so this graph is going to be oscillating So going back and forth over the x-axis, but eventually, I mean, it's going to be going from really, really small values of y to really, really large values of y, and it'll keep switching back and forth. So it's almost like we could say that the graph as x approaches negative infinity will be oscillating between positive and negative infinity. So this limit does not exist. Okay, and I'm going to write because, you move this over a little bit. Oscillating between positive and negative infinity. Okay, so to determine this next limit, you could always graph sine of x over x to see what it looks like the function's doing as x approaches infinity, but I asked us to not use the graphing calculator here. So another way to write sine of x over x is 1 over x times sine of x. Or then if we think about using the limit properties, limit laws, I can rewrite this as a product of two limits. And we already talked about how the limit of sine of x as x approaches infinity doesn't exist because the graph is oscillating between -1 and 1. However, the limit of 1 over x as x approaches infinity is 0. So 0 times sine is going between -1 and 1, so real numbers. And any real number times 0 is just going to be 0. So this limit will actually end up being equal to 0 because of this limit. Okay, so you guys have talked about horizontal asymptotes before, mainly when talking about rational functions. You guys have determined when there's a horizontal asymptote, the function has a horizontal asymptote. A horizontal asymptote is a type of asymptote that describes the end behavior of a function, which is why whenever we take the limit as x approaches positive or negative infinity, if we end up with a limit, that means that there is a horizontal asymptote at y equals to whatever that limit is. Okay, and then just a reminder that horizontal asymptotes are not discontinuities. So a graph can cross its horizontal asymptote any number of times, although they don't have to. And the horizontal asymptote just tells us the y values that the graph approaches. So now we're going to look at evaluating the end behavior of some rational functions. And we're going to do this by taking the limits at infinity. So let's go through these first just by using some of our pre-calc knowledge and just kind of analyzing what's going on with the function. And I'm going to show you kind of another method for evaluating the limits and therefore determining end behavior for these rational functions. So for this first function, notice that the degree of the numerator is 2 and the degree of the denominator is 3. So when the degree of the denominator is larger than the degree of the numerator, that means as x gets very large or x gets very small, the denominator is going to be growing at a faster rate where the numerator can't keep up. So we can say that the limit as x approaches infinity will end up being 0, as well as the limit as x approaches negative infinity. Okay, and we just talked about this definition. This means that this function has a horizontal asymptote at y equals to 0 because we had our limits at infinity existed, right? We ended up with a number, a limit. So there's a horizontal asymptote at y equals to 0. Okay, then for g of x, notice the degree of the numerator is 5 and the degree of the denominator is 5. So they're the same. Now, as x gets very large, so let's think about taking the limit of g of x as x approaches infinity. As x approaches infinity, we can think about the terms in the numerator as being like a tug of war with each other, where as x gets infinitely large, the term with the largest exponent is going to win the tug of war, making negative 8x cubed and the plus 12 really insignificant whenever you have ginormous numbers being raised to the 5th power multiplied by 3. And then same thing with the denominator. So we can really focus in on the two terms, the leading terms of the numerator and denominator. And notice that because we have x to the 5th in the numerator and denominator, as x gets infinitely large, those x to the 5th are going to actually, you think of them as canceling out as x gets infinitely large. So then the y values will always end up approaching this ratio, 3/5. So this limit is 3/5, and as x approaches negative infinity, the limit will also be 3/5. So g of x has a horizontal asymptote at y equals 2/3. All right, h of x. So a different color. Degree of the numerator is 3, degree of the denominator is 2. So the numerator is going to grow at a faster rate than the denominator, meaning h of x is either going to end up approaching positive or negative infinity. But let's do this analysis to figure out which it is. Okay, so as x approaches positive infinity, 4x cubed is going to be giving us positive values, and then negative 2x squared will be giving us negative values. So a positive divided by a negative will always give us a negative, so we'll get negative infinity. And then the limit as x approaches negative infinity for h of x, the numerator would be negative because a negative value cubed is a negative, and then the denominator would be, the negative 2x squared would be negative because of that negative 2. So a negative divided by a negative is a positive, so h of x will approach positive infinity. Okay, meaning there's no horizontal asymptote for h of x. It may have another type of asymptote, but not a horizontal asymptote. So in example C, we saw we didn't have an asymptote. It does, however, have another type of end behavior asymptote, a slant asymptote, which you might remember from pre-calc when a rational function has a slant asymptote. So if the degree of the numerator of a rational function is greater than the denominator's degree, then the end behavior model will be a polynomial whose degree is the difference of the degrees of the numerator and the denominator. So the end behavior model will have the same end behaviors as the original function that you're actually taking the limit of and trying to determine end behavior for. And it will tell us how the graph of the function goes to where it goes. So let's go back through these three functions and determine the end behavior model. So for f of x, our end behavior model is going to be the ratio 3x squared over 5x cubed. And the reason that is I kind of already said it in example B. So as x gets infinitely large or infinitely small, imagine the terms in the numerator being at a tug of war with each other. Well, as x gets infinitely large, that 3x squared is going to dominate the other terms. And then same thing with the 5x cubed. So the other terms we can kind of ignore because we're just worried about what's happening to the values of the function as x gets infinitely large and infinitely small. And they will just not really matter. So our end behavior model is y equals 3x squared over 5x cubed, and that will simplify to be 3 over 5x. Well, 3 over 5x is just 1 over x, being vertically stretched by 3, horizontally compressed by 5. And you know what the end behavior of that function is. So if you were to take the limit of 3 over 5x as x approaches infinity, you would get 0. And if you take the limit of 3 over 5x as x approaches negative infinity, you would get 0. So the function f of x has the same end behavior as the end behavior model. Our end behavior model for g of x, okay, it's going to be the ratio of the terms with the largest exponents. So we would have y equals 3x to the 5th over 5x to the 5th, where those, x to the 5th cancel, so we end up with 3/5. Our end behavior model in this case is a horizontal line at y equals to 3/5. So as x gets infinitely large, or approaches positive infinity, for the horizontal line y equals to 3/5, it would approach it would approach 3/5, and then same thing as x approaches negative infinity. Okay, so g of x has the same end behavior as the horizontal line, y equals to 3/5. For h of x, our end behavior model is 4x cubed over negative 2x squared. So when we simplify that, we get negative 2x. So that's a line with a negative slope, a slope of negative 2. So as x approaches infinity for negative 2x, negative 2x approaches negative infinity, and then as x approaches negative infinity, negative 2x approaches positive infinity. So we found those limits. Now, you may remember from pre-calc, when the degree of the numerator was exactly 1 more than the degree of the denominator, there was a slant asymptote. And there will actually be a slant asymptote that will be like a more, you could think of this equation of the slant asymptote as being a more accurate end behavior model. And we know the first part of the equation of the slant asymptote. It's going to be y equals to negative 2x. We just don't know what the y-intercept is yet. But if you think back to pre-calc, you can determine what that y-intercept is. So let's move to example 3. So what we're going to do first is we're going to actually rewrite h of x in a different form. And we're going to do that by dividing the denominator into the numerator. So we're going to do some polynomial long division. And just remember that bar is a division bar. So we're going to divide negative 2x squared plus 5x minus 9 into 4x cubed minus 2x squared plus 4x minus 7. So for polynomial long division, okay, we're going to focus this term and we go, okay, well, what times negative 2x squared would give me 4x cubed? And that would be negative 2x. And then I'm going to distribute the negative 2x to each term over here. So here, here, and here. So we'll get 4x cubed minus 10x squared plus 18x, and we're subtracting that. So 4x cubed minus 4x cubed is 0. Negative 2x squared minus negative 10x squared will be 8x squared. 4x minus 18x will be minus 14x. And then I can bring down the minus 7. So now I go back to negative 2x squared and go, what times negative 2x squared would give me 8x squared? And minus 4 would. Distribute the negative 4 to each of those terms. So 8x squared minus 20x plus 36. Then we subtract. So that'll give us 6x minus 43. Now if we go and try and figure out, okay, what times negative 2x squared would give us 6x? There's nothing. This is actually our remainder. Okay, so we can rewrite h of x. I'm going to do it down here so I have more room. We can rewrite h of x as negative 2x minus 4. And think about regular long division. We're going to take the remainder, okay, we're going to put it over the denominator. So negative 2x squared plus 5x minus 9. This is just an equivalent form of the equation for h of x. Now, if we were to take the limit as x approaches infinity of h of x written in this way, I'm just going to copy and paste. And we thought about applying limit laws, where I'm going to say that's one piece of the function, this is the other. Notice that the limit of 6x minus 43 over negative 2x squared plus 5x minus 9 is going to be 0, since the degree of the numerator is smaller than the degree of the denominator. And then the limit of negative 2x minus 4 would be, it's a line with a negative slope, so it would be negative infinity. And we've already evaluated these limits, right? Our slant, the equation of the slant asymptote for h of x is going to be y equals to negative 2x minus 4. And what that means is that as x gets infinitely large and infinitely small, the y values for the function h of x are going to be approaching the same y values as the line negative 2x minus 4. So let me show you the graph. Okay, so we have the graph here of h of x. Okay, so you can see there's kind of a little bump about the origin. And if I throw on here y equals negative 2x minus 4, okay. Now close to the origin, the line doesn't really look like it matches up with the graph of h of x. But if we were to zoom out, you can see that the graph of h of x and the line, or slant asymptote, end up looking like they're merging together as x gets larger and larger and smaller. So you can see how the function h of x ends up approaching the same values as our slant asymptote. Now, sometimes the degrees of the numerator and denominator are not as explicit. Okay, this often occurs when either the numerator or denominator are under a radical. So for these types of problems, we can use a similar analysis, so doing the end behavior model. But functions like these may end up with 2 or 1 end behavior asymptotes. So it's important to analyze the simplified ratio of the leading terms to get the value of the limit, but then based upon the type of infinity, so plus or minus infinity, we're approaching, will determine the sign plus or minus of the limit. Okay, so end behavior model here will be y equals to 4x over the square root of 9x squared. So simplifying that, the denominator simplifies to be 3x. Okay, so if the x's cancel, you'll end up with 4/3. The thing is, the limit as x approaches infinity for f of x is not necessarily 4/3. It could be plus or minus 4/3. We need to go back and do another analysis. So I go back to the function f, and I see that because of the square root in the denominator, regardless of what values of x you're substituting in, will always be positive as long as there's real outputs. However, the numerator, because it's a polynomial, could be positive or negative. So I go back here and I go, okay, well, as x approaches infinity, that 4x will stay positive, and the denominator will also stay positive. So positive divided by a positive gives us a positive. So the limit as x approaches positive infinity will be 4/3. However, the limit as x approaches negative infinity will be negative 4/3, because as x approaches negative infinity, 4x will approach negative infinity, but the denominator will be positive. So when you have the ratio of negative over positive, you get a negative. Therefore, we say fx will be approaching negative 4/3. So we end up being able to say that f of x has a horizontal asymptote at y equals to 4/3, and also a horizontal asymptote at y equals to negative 4/3. And if you graph f, you'll see that happening. And if you graph f along with those two horizontal lines, you'll see that it looks like f is approaching those two different values. Okay, end behavior model for g of x. So you have negative 2x cubed over the square root of 11x to the 6th. That will simplify to be negative 2x cubed over the square root of 11 times x cubed, which will simplify to be negative 2 over root 11. But don't get too hung up on that negative that's there. So we know that the limit as x approaches positive or negative infinity will be a version of 2 over root 11, but we don't know the sign yet. We need to do further analysis. Okay, so the numerator, as x approaches infinity, the numerator will be negative because of that negative 2, and the denominator will always be positive. So negative divided by a positive is a negative. So as x approaches infinity, we'll get negative 2 over root 11, which if you rationalize the denominator would be negative 2 root 11 over 11. And then for as x approaches negative infinity, the numerator will give us negative values, because a negative cubed is a negative, and then times negative 2 would be positive, and the denominator would be positive. So we'll have 2 over root 11, or 2 root 11 over 11. Okay, so g of x has a horizontal asymptote at y equals to negative 2 root 11 over 11, as well as a horizontal asymptote at y equals to 2 root 11 over 11. Okay, and each horizontal asymptote helps us to understand what the end behavior is for that function. Okay, for capital K of x, our end behavior model, the denominator ends up simplifying to be the same thing. So root 11 x cubed. So we'll have negative 5 over root 11 x. Okay, well, the limit then as x approaches infinity of capital K of x will be 0 because our end behavior model as x approaches infinity would approach 0. And then same thing as x approaches negative infinity would approach 0. So k of x has a horizontal asymptote at y equals to 0. Okay, so remember, limits at infinity, you're thinking end behavior of a function. And for anytime you have a function that is either rational or it's a function that's written as a ratio, like these are not rational functions. By definition, a rational function is a ratio of 2 polynomials. But you can come up with an end behavior model, which is a simpler equation that has the same end behavior of the function that you're trying to determine the end behavior for. Okay, and two types of end behavior asymptotes that I'm going to ask you to find equations for: slant asymptotes and horizontal asymptotes. And then one last thing, so if you have a rational function where, let's say the degree of the numerator, something like 2x to the 6th minus x to the 4th plus x minus 1 over, I don't know, 3x to the 4th plus x plus 7. Okay, so let's say we wanted to know the end behavior of this guy. End behavior model. Okay, when we simplify that, we get 2/3 x squared. Well, think about end behavior of 2/3 x squared. It's both ends up, right? So the limit as x approaches positive infinity of this guy will be positive infinity. I'm not going to write that down. And limit as x approaches negative infinity would also be positive infinity. So the end behavior of this function is actually more like a quadratic. So we don't say that it has an asymptote. It has a different, more of like a quadratic end behavior. And if the difference is 3 degrees, then the end behavior would be more like a cubic. 4 degrees, it would be like a quartic is the same as a quadratic, and so on.